Thank you, Mr. Chairman, and good afternoon, ladies and gentlemen. Of course, at the beginning, I would like to thank the International Scientific Committee for inviting me to give a talk and present my results. And also, I don't know if I should mention this, but this is my first time when I can visit Opole city, so also for this, I'm very grateful. So today, I will give you the presentation concerning the pulse height analysis system for W7-X. And the outlook of my talk is that first I will give you a very brief introduction to W7-X. You have already opportunity to listen, to hear about this during the first session, and I'm sure that you will also hear about the W7-X during all these conferences, during future presentations. I will try to explain why the impurity behavior studies are important, and I present briefly the W7-X diagnostics and general overview of this. Then I will go to the pulse height analysis system dedicated for W7-X, which is a common project which the system was designed in cooperation with IPP Greifswald and IPPLM in Warsaw. And at the end, I present the exemplary results from the last campaigns, and I summarize the talk. So as you know, the W7-X decelerator is a complicated machine, and this is the superconductic decelerator with such a parameters. So the volume of the plasma is 30 cubic meter. We have the magnetic field around 3 Tesla, 2.5. And the main mission of the decelerator is the steady state operation. So we expect the pulses up to half hour. And of course, the several optimization, which one of this is to show that the optimized decelerator can reach some performance level of tokamaks. And what is important in the device is the magnetic field. We heard today morning also about this, and the magnetic configuration is based on the main helical field, which consists of 50 planar coils. You can see here. These are superconducting coils. There are 20 planar coils, 10 control coils, and 5 trim coils for the correction of the magnetic field. And as you can see here, the cross-section in different places is different, but still you can observe here the magnetic lines and the islands, which were also subject of this today morning presentation. The decelerator already has his its first operation in 2050, and 2060 at the beginning was the first operational phase with the graphite limiter. So these are the main achieved parameters of the plasma. So at the beginning we have only the ECRH heating, and during the OP1-2, the last campaigns, because this OP1-2 was divided in 2 experimental campaigns, A and B, the decelerator was changed from the limiter to diverter configuration. We have uncooled graphite tails, and additional to ECRH, we have NBI heating. And in around 2021, we'll have the next campaign, and additionally with some also ICRH heating. And what I want to mention here that, of course, before the experimental campaign, there are some parameters which is foreseen to achieve. And up to now, all these levels of each parameters were even higher than we expected. So the campaigns were very fruitful in the results, and still there are a lot of data for the analysis. Concerning the diagnostics, so as you can see here, this is the CAD drawing of the W7-X and a lot of ports. Of course, not all of them are dedicated for the diagnostics, but as you can see, there are a lot of possibilities and places for the diagnostics of the plasma. And why we need these diagnostics, and of course, why they are so important, because of the impurity, which we don't want to have a lot of them in the plasma. So the impurity control is very important, especially in the magnetic confinement fusion, and this is because that non-asymmetry 3D magnetic field in the stellarator, which we have, the impurity transport in the core, is expected to be a little different in comparison with the tokamaks. And understanding of this impurity transport is one of the key issues for the steady-state operation. And at the W7-X, there are several diagnostics, especially dedicated for the study of this mentioned purpose. And also, there are some diagnostics dedicated for the injection of the impurity, like gas puff, laser blow-off, test pellet or pellet injections. And here you can the cross-section of the W7-X with the position in the torus around the W7-X of this mentioned diagnostics. So the impurity studies, impurity behavior studies are very important because of accumulation. So we want to avoid this accumulation in the plasma, and also it is important for the long pulses where we want to have the steady state operation. And from experiment, we can monitor the temporal intrinsic impurity emissivities by the observation of the emitted radiation. And also we can monitor temporal injected impurity emissivities and study confinement time and decay time of the impurities. And this is important for the estimation of the transport relevant parameters like impurity transport times, radial electric field, diffusivity, and convective transport coefficient. Here, this is the list of, not all, but the first diagnostics which were installed at W7-X, where we have the interferometer, ECE, filter scope, multipurpose manipulators, and ECRH, of course, for the heating. But in this list, we can select several diagnostics dedicated for the impurity behavior studies. So here are these main diagnostics. This is X-ray imaging crystal spectrometer, high-resolution X-ray imaging spectrometer, VUV spectrometer called Hexos, pulse height analysis, bolometer. And these diagnostics, of course, this crystal, VUV, and pulse height analysis have a energy resolution, bolometer, or like also a tomography system, as are the diagnostics without energy resolution. But to comparing the results obtained from these all diagnostics, we can deliver a lot of information about this impurity behavior in the plasma. So now I will focus on the pulse height analysis system, especially dedicated for the W7-X. So at W7-X, the system consists of a 3-channel, and this is because we want to observe the spectrum in the very broad energy range to deliver information about the impurity from low Z up to high Z elements. So first 2 energy channels are equipped with silicon drift detectors, a commercial one from the PN detector company, and these are this is the picture of these detectors. So this is head silicon. The active surface is like here 10 per 450 microns, and it is covered by 8 microns of beryllium window. And the third one, this is special one, which is dedicated for the observation of light impurities. Also silicon detectors, but with thin polymer window, which can deliver spectra from the range around 350 eV. So how works the silicon drift detectors? So when bias is applied for the detector, it converts each photons which comes from the plasma to an electron cloud with a charge that is proportional to the characteristic energy of these photons. And the electrons are then drifted down between cathode and anode, and then is collected on the anode. And the charge that is accumulated here is converted to the voltage signal by the field effect transistor. And here you can see the concept of the diagnostic. So we have plasma, which reach the detectors. Then we have the charge preamplifier, digital pulse processor, and the data are going to the computer. And what are the details of this all long way of the signal which we register? So the charge liberated by the individual X-ray photon appears at the output of the preamplifier as a voltage step on the linear increasing voltage ramp. And the fundamental job of the pulse processor is to accurately measure the energy of the photon which comes to the detector. And this gives us the digital count in the corresponding channel. And with digital pulse shaping, and the signal from the preamplifier is digitized at the input of the pulse processor, and shaping the noise reduction, and then we have the digital computation. And this time with this shaping of the pulse is very important in the PHA system, because on this time, which we called this as shaping time or peaking time, depends the energy resolution, as I will say a few words more on the next slide. And then the preamplifier output is sampled continuously by the analog to digital converter, and X-ray pulse height are typically measured by subtracting the average of one set of values. And then the resultant value of the step measured in then sent this directly to the PC. Concerning the PHA settings, so we have to choose the interesting energy range. So we can do this by the applying of the additional filters. And in case of the PHA at W7-X, we use the beryllium filters with different thicknesses. So, of course, one of the detectors, as I mentioned, is covered by the polymer window. So we have also possibility to not use any additional filter, only plasma goes direct to this detector. The pinhole size we can set, and this defines as the photon flux. And of course, the peaking time, which define as not only the energy resolution, but as you can see here, this is the dependence, the input count rate, independence of output count rate. So as you can see, for different value of peaking time, we can have the situation that, for example, we have 100 counts per second, kilocounts per second, and for, let's say, 2 microns of the peaking time, we have 2 values of output count rate. The first one is around here, and the second around here. So it is very important to know exactly on which side you are on this dependencies. The best is always to be on this side, that when you then increase the pinhole size, you can increase the photon flux and try to find the optimum position. But still, looking only at this figure, you can say that, okay, let's put the 0.1 microsecond of the peaking time, and we will be almost linear dependence. But as you can see here, there is some border where if you want to have a good energy resolution, so you have to choose something between 1.5, let's say, microsecond. But when you decrease the peaking time, of course, you will have the better statistics because you can observe more photons, but your energy resolution will be worse. And you can, for example, in that case, cannot resolve these helium and hydrogen lines, like it is presented here. So the proper settings of the PHA is a really advice, yeah. So the PHA system, this is the concept. So we have the diagnostics port at W7-X and the main, let's say, component located here, the pinholes, which consist in that case of piezo slits to have the possibility to increase or decrease the photon flux depending on the plasma conditions. And further we have the detectors. And additionally, because depending on what we are interested to observe, we put inside the special filter holders. So for each of 3 PHA channels, we have possibility to choose 3 different beryllium filters with different thickness. So for one channel, we can have 3 energy ranges. The geometry was chosen based on some simulation, because at the beginning, of course, we have to simulate the spectra, what we will expect from W7-X before the operation, and the location of the slits is 7 meters, around 7 meters from the plasma center, and this is also because of the location of the turbomolecular pump and because of the magnetic field. And 1 meter behind the slits, there are detectors. And this is the part of the vacuum chamber with the pinholes, and this is the flange with the detectors. The photo is from the laboratory, and this system was then transferred to IPP and installed at W7-X. Of course, we have to, when we have different diagnostics, we have to think about the calibration. So for the energy calibration of the PHA, we propose the fluorescent spectra. So we installed and designed here, as you can see, the special calibration port, which is presented here. And here we have the mini X-ray tube, which generates the X-ray radiation. And inside this port, we locate the materials for the fluorescence. So this is stainless steel with some additional of copper, aluminum. And here you can see example of this fluorescent spectra, which we collect, and the calibration curve with the energy resolution for the particular energy. As you can see here you have the details of the distances between plasma pinholes, detectors, and also concerning the slits, the pinholes, we can have the possibility to increase the slits up to 1.2 millimeters. Here we have the photo of W7-X stellarator with already installed the PHA Diagnostics. This is the photo from the 2050, and the main vacuum chamber. The PHA system is very useful as diagnostics, which is in operation at many devices. It was in operation at ASDEX, it is at TCV, it was at JET, at EAST. There are tokamaks and also at Stellarator. So the diagnostic is already in operation W7-X. It was at ALHD and TJ2 in Madrid. And what is the differences between these all diagnostics? So at LHD, as you can see, I tried to compare all of these diagnostics. At LHD, the system can deliver the radial profile of the spectrum. So it is very useful that you have, for example, the temperature distribution inside the plasma. But the resolution was a little worse than, for example, now at W7-X. At W7-X, we have only one line of sight, but with very broad energy range, so we can deliver information about the kind of impurities from low Z up to high Z materials. And at TJ2, the resolution, temporal resolution is very good, 10 microseconds, but the energy resolution is much worse, 357. And similar in all diagnostics, at all of these devices, we apply different filters to change the energy range of observation. And the main purpose of this system is, as I mentioned, identification of the plasma impurities. So from the observed spectrum, we can identify the elements. We can determine the impurity density, comparing with the simulations. We can determine the electron temperature from the slope of the observed continuum radiation. We can determine the Z effective and study of non-Maxwellian tails, suprathermal electrons, if of course present in the plasma. So this is the photo of the W7-X inside the vacuum chamber with, say, expected impurities. And now a few words about this, each purpose of the diagnostic. So identification of the plasma impurities. Here you have the examples of the spectra collected during the OP1-2A campaign. As you can see here, we have the fluoride, argon, chromium, iron, nickel, copper. And also, this is the third PHA channel, the spectrum observed by this detector with polymer window. We observe here the oxygen, and also we really very want to observe the carbon line, but still this is question mark if we observe the carbon or some noises of the detector. And of course, after the identification, we have to confirm this identification. So as you can see, this is the example of the spectrum observed by the VUV spectrometer Hexos. So all the lines which we identified were visible also in the spectra collected by the spectrometer. And the table with all listed elements with also injected impurities in the plasma. Determination of the electron temperature. So as you know, the continuum spectrum consists of the free and free bound radiation, which can be written like this. And we can see here that this is the exponential dependence on energy. So in these equations, we have electron temperature, electron density here, and the charge Z and Gaunt factors. This is the parameter which can be taken from the literature. And we can rewritten this equation in the dependencies. So in the logarithmic scale, we have the linear dependencies, and from this linear fit, we can determine the electron temperature. So this is very common in all of the devices method for this electron temperature estimation, but you have to remember that this is average electron temperature integrated along the line of sight, because we calculate this from the spectrum, which is average over the line of view. So determination of the Z effective. So Z effective is proportional to the emissivity, and this is the parameters which can be taken from other diagnostics and also from calculation. So if we have the dependencies, electron temperature and density from, for example, Thomson scattering or ECE or other diagnostics, then we need this emissivity of the Bremsstrahlung radiation. This is important because, as you know, normally the Z effective, usually such a diagnostics is in the visible range, and here we have X-ray region. So so this is some method for the estimation of this parameter. And how we can find this emissivity? So the number of photons of the given energy, which is emitted by the point inside the plasma, inside a solid angle, can be written like this. So this is proportional to the emissivity of this irradiated point, the volume, time, and energy. So all the points located inside this cone, it is a sum of this equation. So the average emissivity as a function of the collected number of photons can be written like this, where I add here the two parameters. A is a geometrical parameter, let's say, which depends on the size of the detector and the cone of view of the plasma, and the M parameter, which includes the pile-up effect, because when you have a very high in photon flux, there is a possibility that you don't observe each of the photons which comes to the detectors. So we can include also this pile-up effect. We should include in the estimation of this emissivity. And what I want to also mention here, that in our spectrum, in the PHA spectrum, you normally observe the free and free bound radiation. So you have to exclude, from the simulation, this free bound radiation to include only the emissivity of free to calculate the Z effective. So this is the method which we use and will be used for the estimation of the Z effective at W7-X. Study of the non-Maxwellian tails. So in a uniform plasma, after the many collisions times, thermal equilibrium is achieved, and the amount, when the amount of these electrons that are much faster than the others, so we have some additional tail in this Maxwellian distribution, so then we can say that there are suprathermal electrons in the plasma. And this is example taken from the paper of von Goller from ST tokamak, where it is presented how we can see this from the PHA spectrum. So you have the linear dependence from the thermal continuum, and then you observe this runaway tail. And at W7-X, up to now, we didn't observe these suprathermal electrons, so I just want to present you only the possibilities and the main purpose of the system, how we can determine such a non-Maxwellian distribution. So as I mentioned, the PHA consists of 3 channels, and during class campaign, we used such a beryllium foils, and we had 3 energy ranges for the observation. So the first channel was equipped with the additional 1 millimeter of beryllium foils, so we observed the spectra starting from around 3.6 keV. And second was equipped only with this 8 micrometer of beryllium window, so it was dedicated mainly for the observation of this medium Z elements and the Bremsstrahlung radiation. And the third one, without additional filters, only covered by this polymer window. And here you can see the detector response curves for all of these 3 detectors, where I selected also the position of the main impurities which we foresee for the observation. So you can see that, for example, the first one, the detector were dedicated for the observation of high Z elements. So some examples from the last, actually 3 campaigns. From the first campaign, OP11 experimental operational phase, we performed study of the impurity behavior for the first magnetic configuration changes. So we chosen 5 discharges, each with a different value of iota. So you can see here the point car plots of the vacuum magnetic field, where the position with the position of the PHA in line of sight. And as you can see, we can observe the changes of this magnetic island on this picture. So the scan of this magnetic configuration were performed with the various of the planar coil currents, and with increased iota, these 5/6 islands were moved inwards, as you can see from these plots. The waveform of this typical 5 discharges which we analyze is presented here. So during this OP11, we have the limiter configuration in hydrogen plasma with the magnetic field at level of 2.5 Tesla. We have 3-step of the ECRH heating. We have the line integrated electron density at level around 1.6 times 10 to 19 square meter, and the pulse length were around 1.2 a second. And what we observe, here you can see the spectra observed by the PHA system. So no significant changes of the impurity intensities are observed in these iota scans. You can see that they are almost the same. Only what we can observe, there are a little changes in the argon, but it could depend on the amount of puff. And difference in the impurity intensity is observed only when we change the ECRH power, as it is expected, I guess. And a higher relative, of course, concentration of argon is observed in the plasma in comparison with the sulfur and chlorine in that case. And in this performed experiment, there were core electron root confinement conditions, which is characterized by the central peak electron temperature profile together with a flat electron density. And ion temperature profiles also were observed, and the electron temperature was much higher than an ion temperature. So in this TERC conditions, the formation of a positive radial electric field in the plasma core is expected. And the radial electric field is mainly given by the electron temperature gradient in the center of the plasma. So we calculate this temperature gradient and plot the argon line versus this gradient. And what we observed decrease of argon W7-17. So this is helium-like argon line integrated intensity with the gradient of electron temperature. What could suggest and could be an indicator of the decreasing diffusivity with radioelectric field at low collisionality of impurities and change in impurity transport. But of course, this requires the quantitative impurity concentrations, not the relative one, and it is still under investigation. So the next example which I want to present you, this is during the last campaigns, system for the injection of the different kind of impurities were commissioned and tested. So it is the laser blow-off system and the test cell system, tracer and globe solid pellet system. Both of this system can deposit materials, different materials inside the plasma. The laser blow-off mainly in the edge and the test cell in the core. And during the last campaign, it was also possible to inject by the test cell not only single tracer inside the plasma, but also triple one. In that case, it was manganese, vanadium, and nickel. And the results, the PHA Diagnostics, of course, can confirm the deposition inside the plasma by the observation of the particular impurity lines. And here you can see the example of the laser blow silicon injection by the laser blow-off system, titanium and iron. And also we can observe the behavior during the discharge of all of these elements. And this is the blue one signals here correspond to the PHA data, and the red one belong to high-resolution XISCS spectrometer with very high time resolution. But still, as you can see, we observe similar behavior even with not so high temporal resolution. And example with the test cell injection, so the spectra with the copper injection when inside the test cell were copper, and also this triple tracer impurities. As you can see, we can observe very nice helium-like lines, ion lines here, and also we can observe the decay time during the discharge for all of the injected impurities. Also, the last example of the observation which were done during the last campaign. So we have the discharge with the laser blow-off injection and also with the test cell injection. And in that case, we observe very, in comparison to the laser blow-off and in comparison to the previous observed test cell injection, very long decay time, which could be correspond to this sudden increase of the ECRH power, because this is the correlation between this, but still we need some detailed analysis and including also the electron temperature and density behavior during the discharge to explain this behavior. And other application of the PHA and what kind of data it can deliver. So during the last campaign, there were the boronization process at W7-X, the boronization of the graphite wall. And we observed here that after boronization, the level of the oxygen was decreased around 5 times in that case, which I present here. And as I mentioned, we really want to observe also carbon, but still this line behave little different that we expect. So we are not sure if this is carbon. So summarizing, the PHA deliver information about the kind of the impurity of the plasma, especially at the at the W7-X with its temporal resolution. The system can present the trend in impurity behavior during the discharge and can be a confirmation of the observation by other diagnostic. We observed the long impurity transport time of injected impurities during the ECRH power changes, but still this is under investigation. And based on the PHA, we can study the Z-dependence in the same experimental conditions because of its broad energy range. And we can observe different lines from different elements. And what we achieved during last campaign, we achieved a resolution of 50 milliseconds. So this is also good temporal resolution to observe any changes in the impurity behavior. And the PHA spectra observe the changes in oxygen emission before and after boronization. So they confirm that the boronization decreased the level of the impurities level in the plasma. Thank you very much for your attention.
Thank you very much for a very interesting talk. Now we have time for the question. Yes, please.
Yeah, thank you very much. Very interesting. I have actually two questions. First, on the test bell. What is the main purpose of the test bell system? So, in principle, why do you need to detect the elements like vanadium and manganese in the core of Wendelstein?
Actually, these are we can implement inside different kind of elements, but vanadium, manganium, nickel, and these elements which were already injected in W7-X were also injected at other devices like LHD, for example. And this gives us the possibility to also observe especially in the PHA system, we have the energy range which give us the possibility to observe this helium-like these exactly ions, yes? So the elements which is injected is first, I think, discussed by with the people from the diagnostics, and of course we will not inject the elements which we cannot observe. So these elements are very good for the observation and also very well, yeah.
Can I comment?
Yes, please.
I could tell that are you asking why those elements? Mostly because they are not in the Wendelstein yes. Normally. So you know that they are only from the test bell, and you can study how long, for example, they survive inside.
Not only because iron actually is somehow but this is also in somehow when you additional inject iron, it is also needed, yes, to find some behavior of these impurities.
And the second question, if I may, can you go to the slide when you're shown, I think that was a comparison of LBO on one of the previous slides. It is at the end with 1/3 of where you had the blue and red, yes, exactly. So, I mean, it looks like the temporal resolution is fine, however, the amplitude is very much different.
But the PHA emissivity we calculate using, and this is not calibrated signal. But in that case, even the PHA, now it was, okay, here it was 100 millisecond resolution. Now we achieve better 50 milliseconds. That is why I didn't present the comparison between other diagnostics, but now the results are better and fit better with other results.
Do you have another?
Thank you for the detailed description of your diagnostic tool. I was wondering about, you also mentioned the crystal spectrometers, the tools based on the use of crystal spectrometers. Do you have any experience in it, maybe?
Not person, no.
Oh, okay.
But this is...
I was wondering, for example, what kind of spectrometer geometry do you use? But okay, I will
think
discuss.
this is Johann's spectrometer.
Johann,
Yeah.
Johann, okay, thank you. And maybe one last question is, you mentioned that you also model the spectra, of course. What kind of software do you use? I guess you need some software.
Concerning the PHA, we develop our own software. This is the special code, very simple 1D at the beginning with only the coronal equilibrium assumption. And we, based on this code, we design this diagnostics. Yes, knowing the foreseen W7-X scenario, we calculate the expected spectra. Then we calculate the photon flux which we expect, and we can design the geometry. And now we further develop this system to include also the transport, impurity transport. But
is this code published somewhere so I can read about it?
Yes.
Okay,
yes,
thank you very much.
In Journal of Instrumentation, I think, the Ray X code it is called.
Ray X code, thank you.